Now, you joined in the 90s, but Neumann has a history that dates all the way back to the 20s. Can you give us maybe some of the main milestones of the company along those years?
Even before George Neumann founded the company, he worked with Eugen Reis, or he learned in a company called Mixing Genest. He learned as a mechanic, became interested, or in a company that was involved with early electroacoustics. And then in working together with Eugen Reis, he invented what I think was one of the last steps in development of the carbon microphone. A special marble block square thing, which then Eugen Reis patented in 1925. And then George Neumann himself became more interested in record cutting, vinyl cutting. So the carbon microphone that was marketed by Reis was nice enough, let's say 300 hertz to 5 kilohertz, almost linear, sort of. High quality for that time radio broadcast, but could be improved. And there was this other principle, condenser microphones, capacitor microphones, invented in 1916, already first patent on that, and which then George Neumann became interested in and thought that could be a nice and suitable microphone for my disc cutting lathe that he was in the process of inventing or developing. And so he built himself his first condenser microphone. He didn't invent the principle, but he was a very capable mechanic and had some very nice ideas on mechanics and fine mechanics and how to do things mechanically, acoustically. And so designed a capacitor capsule, which was more suitable to the real world than the earlier capacitive microphones that were already around, which were more measurement lab microphones. You need to be very careful with handling them. And he found a way not to use, let's say, metal diaphragms, but to make his own diaphragms out of the available insulating materials at the time, making his own membrane materials, and gold sputtering them, and then applying them to a nice electrode and realizing that the frequency response was much nicer than everything he had gotten from the carbon microphone before.
Wow. So that had huge implications on music and on radio, because what was once a measurement microphone that could only be used in a very controlled environment for a very industrial purpose was now something that you could use for pretty much anything.
Yeah, you could produce it in certain quantities, small quantities, of course, at the time, because that's when he decided to found his own company. That was in 1928. That together with Rickmann, he founded his own company and employed 3 colleagues that he had known from his earlier jobs, and started to produce in small quantities disc cutting equipment and microphones, and found that the national radio company in Germany at the time, the Reichsrundfunkgesellschaft, became interested in this microphone and realized it was good and approved it. And okay, federal, national radio station, everything centralized, and you were only allowed to use stuff there for the holy radio thing when the material you used was approved by the technicians from the broadcast company. And so already in 1931, 32, around that, you find the first official sheet in the official book with a page saying, okay, this is the Neumann CMV3 microphone, as it was called here at Neumann, the so-called bottle, with this and this capsule, and this is officially proved to be used by national radio.
Wow. And that's only the beginning.
And that's the beginning. That's when everything started. So the first capsule was an omnidirectional microphone, already very nice, fit to use. Worked, I think, up to around about 12 kilohertz or so, but with a rather pronounced peak, something like plus 12 dB at 10 kilohertz, so very bright sounding, which might have been good for broadcast at the time and record cutting at the time as well. But already 2 years later, there was a second capsule with a much flatter response. And then the next big breakthrough was in 1935 when Brownell and Weber from National Radio Company thought of a way how to produce with the same principle a cardioid microphone, a cardioid capsule. And that's what then in around about 1935 was patented and is ever since known as the M7 capsule, which then after the war, later after a redesign turned into what we now call the K47, K49 capsule, which already from the name you can tell this capsule might be inside the U47 and the M49 microphones.
Yeah, and that's a capsule that's still commonly
in production
spoken about and produced today.
And with the same hole pattern and the same diaphragm distance as, I'm not certain about 1935, but I definitely have still the drawings from 1941 where it says explicitly, okay, the diaphragm distance has got to be like this and this, and we still have the exact same diaphragm distance. Then around about 1924, the ribbon microphone was invented by people working at Siemens and patented it as a ribbon microphone and ribbon loudspeaker. If you have two transducers, one omnidirectional, one bidirectional, combine them, you get what we know as the cardioid characteristic, but you need two transducers in one housing. One could have done that with condenser microphones as well. Develop a figure of 8 capsule, which was actually invented also or developed by Neumann in the early 30s, the so-called M8 capsule, and combine that with an omnidirectional capsule. But then you need two capsules, double the price. You have to combine them in one for one amplifier. So the problem was solved mechanically by realizing a backplate pressure transducer, an omnidirectional microphone. If we make the backplate very open, the sound can come from both sides, we get a bidirectional. Okay, what happens if we just close half of the holes, if we make it half open? You can do that. You obtain something which I would call a really bad cardioid, which might work at 2 frequencies, and for the rest it will not work nicely. But then Brownell and Weber realized, okay, we have this half-open construction with half of the holes being open. What happens if we put a second diaphragm on the other side, on the rear, so the sound cannot really go through, it has to pass through the diaphragm? And then realized that the result was a rather nicely working cardioid tending towards supercardioid capsule, which was then patented and called M7. This capsule is basically the basis for all double diaphragm capsules. If we continue with what happened with these sort of capsules, it was then realized, all right, we have this second diaphragm on the rear. So it was basically symmetrical construction. One electrode, one central electrode, 2 diaphragms. Okay, we can use the front side and the rear side. What happens if we connect 2 sides together? We get an omni. What happens if we connect the 2 sides together, but with one opposite polarity? We get the bidirectional. So there was the option to produce with one capsule, with one double diaphragm capsule, multiple patterns. And that was then realized in the U47 capsule, microphone, where you could switch between omni and cardioid pattern. And this design was further developed then for the M49 microphone, where you can continuously change the addition, the summation of the 2 signals. So on the power supply, there was or still is, as we still manufacture it, or again manufacture it, a potentiometer where you can increase the voltage on the rear side and continuously change the pattern from omni, subcardioid, cardioid, supercardioid, hypercardioid, figure of 8.
Wow. When were these two discoveries, or when were these two inventions, between the omni cardioid figure eight or those variations in between?
The switchable omni to cardioid, that was realized already in the early 1940s, but more like lab samples. So the real first available product with that possibility was then the U-47 microphone, which started shipping in early 1949. First of all, the German broadcast companies, which are all, at the time, were all national or being in the federal states, or the different in the different German federal states, and similar situation also, I guess, in Austria. But also we have in our files quite a lot of test material from, for example, the BBC, who then, 1954, I think, analyzed their first M49 microphone, had a sample, tested it, measured it in all the ways the BBC would test such a microphone, and then write a 20-page report on it with very nice drawings, very nice figures, very nice curves, measured curves, and then recommending or not recommending such a microphone if it was worth it or to look at, or if it was recommended, and for which sorts of broadcast it was recommended to be used by the BBC. And so that was the infinitely or remotely controllable variable with a potentiometer polar pattern.
So it sounds like we came from the carbon microphone to a capacitor microphone. That was the first big step. And then we started thinking, well, how do we know how to do omni, we know how to do bidirectional. How can we get these other polar patterns of directionality? What was the next step?
And then the next step was two things happening sort of at the same time, around about in the 50s. I mean, what came around was television and stereo. So in 1956, the first stereo microphone came from Neumann. That was the SM2 with two small double diaphragm capsules in one housing on top of each other. So they're very close to each other, both remotely controllable with this M49 principle from the power supply, and rotatable in between each other. So you had a sort of what we call an XY setup, one capsule looking left and one capsule looking right. And you combine them, could record a stereo signal left and right with that.
Yeah, and it sounds like you could also then do a Bloom line with the two bidirectional.
Set it to bidirectional, you get a Bloom line. Set it to double cardioid, left and right. Or the second was often also used in broadcasts just as a simple double microphone, one to be used and the other as a backup, just in case something happened with the first channel and you were live on broadcast. So you would still have the second capsule there in exactly the same position. And which was quite often, we're talking about late 1950s, first recordings. I mean, in those days, you still recorded orchestras with one microphone, quite often hanging from the ceiling somewhere over the conductor, or also big band recordings with one microphone, and the trombone player would then walk up to the microphone for his solo quietly while the others were playing and play his solo, then return back to his seat and you did the mixing, by walking. And okay, one typical setup then was that you would have a nice concert hall, or especially in radio halls. There would be a selection of SM2 microphones hanging 5 meters from the stage, 10 meters from the stage, 20 meters, 30 meters from the stage, fixedly cabled there with their remote control power supply and polar pattern switch. And the sound engineer doing the broadcast could then choose for the evening, all right, I'll take the second microphone, which is hanging at 10 meters, and you wouldn't have to climb up there and change everything. He could do it all from his seat. And then in the early 1960s, so-called field effect transistors became available. And these proved to be the first viable option to replace tubes and put a field effect transistor instead inside microphones and make things much smaller and much more handier. The first microphones, transistor microphones, early 60s, which were built, had this powering system, which is most often called AB powering. AB for the two conductors, A and B. It's one of the funny things happening in audio development. There came the occasion that a colleague from Neumann visited the Norwegian broadcast, national Norwegian broadcasters, and they said, yeah, they were interested in these new transistor condenser microphones. And this 12-volt AB powering is nice, but wouldn't it be possible? They had a safety backup voltage system there at Norwegian radio and TV, and they used 48 volts DC. Wouldn't it be possible to power microphones with that as well? And the colleague brought the idea back, and our colleagues here in Berlin picked up the idea and said, okay, 48 volts, that's nice. We could use that for polarizing that's much better than 12 volts. We could use that for polarizing the capsule. And okay, we don't need 48 volts for the circuit, but it's plenty and sufficient, and made a circuit around that. And sent the first microphones to Norwegian radio, and they were happy with it and ordered quite a lot of them. So first customers and first samples went to Norway in this case. And why 48 volt? Because the Norwegian radio happened to have 48 volt backup system. So with a 48 volt system, we apply the plus for the 48 volts to both conductors, and we use the third connection, typically the shield, as return. So we've got a closed circuit. But regarding the signal conductors, both pins going into the microphone have the same voltage. And if we connect a dynamic microphone to it, it says, okay, I'm a coil, but I see a voltage, but it's 48 volts at both ends of the coil. So there's no current running through it. So dynamic microphone won't be damaged or the diaphragm moved by applying this voltage. And so it was a compatible system. And then there was a very long discussion between different microphone manufacturers, different broadcast stations, and I think I've got over 120 pages of copies and literatures and letters going between the different institutions and the different manufacturers and trying to agree, okay, which powering system shall we use now? Both powering systems were standardized in Germany, but in the end, as history tells us, Phantom Power won because it was the more compatible version.
So let's rewind. I want to get back to this development. We had the carbon microphone. We moved into the condenser or capacitor microphone. These are powered then by tubes. We started to introduce the smaller form factor, the stereo microphones, and then we move into the FET microphone, field effect transistor, rather than a tube. And that's what the U87 works upon. Is that correct?
Yeah, I mean, the U87 did have a predecessor, the U67, from 1960. Still a tube microphone. That's where the typical shape that we know from the U87 now came from. The sort of slightly conical housing and the typical shape of the head grill that we also find in this small microphone here, only slightly smaller and nice to look at. And the transistorized version of the U67 then became the U87 in 1967. And so the first large diaphragm transistorized condenser microphone, and then also the small tube microphones were transported to their transistorized equivalents. So the 60s, early 70s were very busy with taking all the existing microphone types and making transistorized versions out of them. In the evolution of microphone circuitry is, okay, things became louder. In the old days, it was typical to have one microphone 10 meters, 30 feet away from the orchestra and picking up everything. Then I think something called rock music came. Things tended to become louder. people tended to starting to use spot microphones, to put microphones on drums or in vicinity of drums where things become really loud.
Yeah,
And
as
realized,
the advent of multitrack became more
and
prevalent, right?
multi-track, first 2-channel options. I think Les Paul had a 3-channel recorder, as I'm correct, 3-channel tape machine, and then 4-channel, 8-channel, 16, 30, 32, whatever.
Yep. So at this point, just to clarify, instead of having one microphone that's far away from everything in order to capture everything, we were able to have a different track on tape for several different instruments and put a microphone closer to each source.
So by the mid to late 60s, it was typical, let's say, to have one microphone on the bass amp, one microphone on the guitar amp, or on the 2 guitar amps by the 2 guitarists, one on the Leslie cabinet, and 2 over, let's say, hanging over the drums as overhead microphones, giving all these channels and all giving loud signals. And then people realized, all right, the tube microphones were not made, the circuit was not designed for these rather high sound pressure levels, and started to distort. Okay, a bit of distortion is nice, especially when we're talking about tubes, but if it's too much distortion, then you don't like it, no matter where it comes from. And so microphones had to be designed which could handle higher sound pressure levels, higher SPLs. And in our case, for example, the first one which could handle really high SPLs was the U47 FET. Transistorized version of the U47, still with an output transformer, but with a really large one, a heavy one. And with for that time, really complex circuitry, which was able to handle up to 145, 150 dB SPL, which was a first for capacitor microphones, for professional capacitor microphones. And so you could really put that microphone in front of a bass drum and get a clean signal. And in front of a bass drum, we do get 150 dB SPL. We're very close to the hole in the resonant drum head. And the U47 could handle that. And that's funnily one of the main applications this microphone found was standing in front of the bass drum. It was the first microphone which could handle something like 125, 130 dB dynamic range, and this became the standard then. With all microphones to follow, especially the TLM ones then, they should be able to handle at least 135, 140 dB SPL. Not putting all the microphones perhaps directly in front of a bass drum, but where you can place most microphones where things can really become loud, and the circuitry can handle that, and you get no distortion. They're clean. And if you still do want a tiny bit of distortion, then perhaps use some of the older or newer tube microphones to get a bit of this tube distortion, which can be nice when things become loud and to make it still more present. Okay, in the mid-70s, there were the first attempts. We already had stereo. First attempts at surround. I don't know if anybody remembers or heard of quadrophony. Quadrophony, I think, lived between 1973 and 1977. Or regarding the German market, it was widely publicized in 1973 on the International Broadcast Exhibition in Berlin. The newest thing, 4 channels. And 2 or 4 years later, nobody spoke about quadrophony anymore. It was too early for that. People had just started changing their record players. Had realized everything had become stereo. And so there was a fight between different companies and from different countries. Nobody agreed on what should be the basic principle that everybody would use. And
it just never really caught on, right?
And the audience wasn't really there yet. It was too early.
So what happened then after quad? What are some other keystone developments?
So keystone development then, around about early 80s, mid 80s. Yeah, transistorized microphones, yes, but still using a transformer for the output. Up till the 70s, all microphones, all condenser microphones had such a transformer at the output. It's very nice. Can be a very good piece of equipment. It's also typically very expensive. It is, to be really good, to be able to handle loud signals, it has to be very big or rather large, difficult to fit into a tiny microphone. How could one get rid of such a transformer? And that's when electronically balanced outputs came into being. That, okay, if we make a balanced output, let's say we need two transistors to drive one, the positive part of the signal, and the second inverted transistor for the negative part of the signal, or for the inverted part of the signals, we still get a balanced output. And we can do it with transistors, and we don't need the transformer.
This is where we come into transformerless microphones.
That's where we come into transformerless microphones, and that's also why this small microphone here is called TLM, standing for transformerless microphone, TLM 102.
I'm interested to hear your perspective as a microphone developer for probably the greatest microphone company of all time. Microphone technology, speaker technology, though they've evolved in the ways you've described, even all of those technology steps have remained relevant. What, if any, future developments do you expect to see in microphone technology?
Admittedly, I mean, condenser microphones have been invented in 1916. So that's over 100 years ago. And we ourselves have been doing microphones for 95 years now, condenser microphones. And so a lot has been invented already. Regarding capacitive microphones, at the moment on my desk, I don't have any revolutionary new idea that will change the world. Instead, it's mostly looking at what do we have already, and are there specific and new applications where new other microphone models might come in handy. Not reinventing the wheel from zero, from scratch, but where typically would say, okay, we need such and such a microphone. It's like specialized microphones like ambisonics microphones, where when we come to VR and augmented reality and 3D recording, you would need something like 4 capsules looking in totally strange different directions on a tetrahedral setup. When you make a microphone like that, you don't have to invent a new capsule. You don't have to invent a new circuitry. You just need a specialized arrangement. You have to choose which capsule is best suited to get 4 of them as close as possible to each other. And okay, we've got a selection of circuits. Should we make a circuit with 4 tube electron tubes? Nope. And 4 output transformers? Nope. So we take a transformerless, transistorized output circuit, 4 channels. Then which connector was already used for which applications? If we use this connector here, will it be compatible with the other users? Is there any danger that this connector being used for another application, that this supply might damage this other microphone? So it's working with the tools that we already have and make new combinations.
To meet the demands of how it's applied, right? All the way from the beginning with carbon microphones, they had a lot of noise, not too great of a frequency response. Then vinyl allowed for a much higher fidelity signal to be recorded, so the microphones had to adapt. And then
came
on and on, right?
Close miking, dynamic range had to move towards higher sound pressure levels.
Yeah, people used the things differently, and so the technology adapted accordingly. It's very interesting.
And then, of course, all right, for us, it's not new technology, but one of our last products was for us a new technology, or the first time we put into the series microphone, the prepolarized MCM instrument microphones. Tiny capsules with a selection of clips, so you can clip them on the different instruments for close miking, basically all orchestral and popular music instruments. And making a new capsule still a condenser capsule. So this was not new, but making a tiny one, which will work nicely, which is able to handle very high sound pressure levels, because it's such a distance from the trombone, it can become very loud. And try to make it sound nice for all instruments. So we don't need, let's say, 12 different capsules, one for the oboe, one for the violin, and the other one just sounds fine on the double bass. But one capsule which serves all instruments equally well. And then make that also available for wireless systems. One thing we didn't talk about yet. All right, so not connecting to phantom power, where we get 48 volts and everything is fine, balanced signals. Nope, connecting to wireless transmitters, pocket transmitters, with their small jack connectors or small tiny XLRs, or whatever the wireless manufacturer chose to use as connector. And they don't supply phantom power, they supply something in between 3 to 6 volts, so minimal voltage, and some of them minimal current. So you have no energy and try to work a microphone with that. And that's where the prepolarized principle comes into play. That definitely when you want to connect to wireless microphones, you have to use prepolarized capsules where there's an electret layer on the backplate, and you don't have to apply the high tension externally. And that's where we became first involved, with the prepolarized capsules.
I'm excited to see where that goes.
The colleagues in production were quite familiar with that, but we had some new ideas there, because they have been working with prepolarized already for quite some time, but we had some new ideas there regarding how we would make it. Different developers, different approaches, and that's a good thing that we've got different brands in our group with different development teams and working in different countries and different ideas coming sometimes from different sides, where we sort of merge ideas coming from all sides, or get inspiration also from other people.
You merging technologies, right?
Yep, in this case.
I appreciate all your time.